Hi students, in this lecture I am going to discuss problems based on motional EMF and Faraday's law. Let us see first one. Given a wire frame, its width is d, mass m, resistance r, and given large length and field is uniform, a constant force starts pushing the frame into the magnetic field at t equal to 0. See what we have to calculate. Find the acceleration of the frame when its speed has increased to v. Show that after some time, the frame will move with a constant velocity till the whole frame enters into the magnetic field. Find this velocity v0. Show that the velocity at time t is given by. This is what we have to show, right? Let us see how to start. Let's first make the given diagram. See what is given here. Given long wire frame, you can see this is now wire frame. Applying a constant force, that is left side, and we can see field is now into the board. It is left of this line, okay, and we can say time t equal to 0, it is about to enter, right? And see what else given here. It's mass m, resistance r, and this width is, that is given as d. And see what else given here. Right, now we can see force is a constant. So first we have to calculate acceleration of the frame when its speed increased to v. So initially speed was 0. When speed is increased to v, what is acceleration, right? Then see what we can say. When speed is v, I am taking here motional EMF. So E equal to L bar dot V bar cross B bar. And if you observe, for this side and for this side, L bar and V bar both are parallel. Okay. So across these two, no EMF is induced. Now EMF is induced only across this one. Okay. And coming to this one, it is not in the field. So only this is now in the field. So across this EMF is induced. So L bar and V bar and B bar is into the board. So all three vectors are mutually perpendicular, right? So EMF is now BLV, right? Then you can see force acting on that wire. I can say magnetic force F suffix B, that is equal to ILB. Okay. Now I value E by R. So E by R into L into B. And E value, it is BLV. So this becomes now B square L square V upon R. This is magnetic force. And you can see this force is now right side. That force is now right side. Cross check once. First, we have to focus in which direction current is flowing. Is it a clockwise or anti-clockwise? So here, when this loop is entering, because of increase in area, flux is increasing. Because of increase in flux, current is flowing. Okay, it is because of increased flux. So now what happens is, because of induced current, magnetic field must be outwards. Okay, so that it is able to decrease the flux. So it is outwards means keep thumb outwards. Thumb of right hand outwards means towards us and curl fingers. Okay, then current will be, it is anti-clockwise. So current will be anti-clockwise. Okay, right. And let us take this board plane as XY plane. Then you can see direction of L bar. When you want to find out force, F bar equal to I into L bar cross B bar. Direction of L bar is direction of current. Current is now like this. That means it is now along negative y-axis, right? It is along negative y-axis. Therefore, L bar minus J cap. I am focusing only direction part. Minus J cap cross B bar. B bar is now minus K cap. It is into the board. So minus minus plus J cap cross K cap. It is I cap. I cap means force is now right side. That is now direction of magnetic force. Okay, right. So now we can see what is net force. Net force is this applied force minus magnetic force, right? So F minus, it is now B square L square V upon R. This net force equal to mass into acceleration. Okay. So first we have to find acceleration. So from this we can get acceleration, that is A equal to FR minus B square L square V upon MR. That is now acceleration, right? And see next what we have to calculate. After some time, the frame will move with a constant velocity till the whole frame enters into the magnetic field. Find this velocity V0. See, velocity constant means acceleration equal to 0. When acceleration is 0, that means this is now 0. Then see what we can write. F is balanced by B square L square V naught. This is given as V naught upon R. Right? Condition is net force equal to 0. From that, V naught equal to FR upon B square L square. Okay. Next. See what is the next one. Show that the velocity at time t is given by. So we have to find velocity as a function of time. Then see what we are doing here. I am writing in this equation. In the place of A, write dv by dt. Okay. So I'm writing here F minus B square L square by R. It is a constant. I'm taking as some constant K. Kv, that is equal to M into, in the place of acceleration, rate of change of velocity with respect to time. Now see what we can write. M into dv upon F minus kv. That is equal to dt. Right? So here what is K? I have taken K as, I am writing here K equal to B square L square by R. Okay. Right. Now integrate. Now when you integrate at time t0, velocity is 0. At time t, that we have to calculate V, right? Now see what we can do here. we can multiply and divide with minus k. Okay, then we get m by minus k for remaining part ln f minus kv, right? Now take limits f minus kv, take lower limit by f, because log a minus log b is log a by b. Okay, that is what I have taken here. That is equal to t. Now simplify this. 1 minus. So I have taken this part to here and take anti-log 1 minus kv upon f, that is equal to e power minus kt by m. Okay. So I have taken this value right side and then I have taken anti-log. Now from this what we can write? From this v equal to f by k into 1 minus e power minus kt by m, and see what we have to prove. So this is, he is saying v naught. Check it once, what is v naught? F r by b square L square, right? What is k? V square L square by r. So f by k, it is nothing but v naught minus 1 minus e power and c. It is ft by m v naught. In the place of k, substitute the value b square L square by r. Okay, b square L square by r. In the place of that, what we can write? It is b square L square by r. This we have taken as k, right? K. We have to show that e power minus ft by m naught. ft by, sorry, ft by m v naught. So in the place of k, or let me do calculation separately here. What is the value of k by m? Okay, k by m, that is b square L square upon r, and this is m. I have to write this in terms of f and v naught. Okay, see here what I can say here from here. Here b square L square by r, that is equal to f by v, right? This is equal to f by v naught, f by m v naught, right? That is what we can substitute here. That becomes f t by m v naught, right? So first we have taken what is the force acting, then we got net force. Net force is mass into acceleration. When acceleration is zero, velocity constant. And next asking velocity as a function of time. Then writing a value dv by dt. And remain just calculation part. Okay. Let us see next problem. Let's see the question given. In the figure shown, the wire is found to be in equilibrium. So wire is in equilibrium means its weight is balanced by magnetic force, right? Because the current is passing like this in the wire, right? So equilibrium, weight mg downwards. Then magnetic force must be upwards to balance that. If the wire AB is replaced by another wire of double its mass, how long will it take in falling through a distance equal to its length? Right. See, the first of all, the given condition. First condition given that the wire was in equilibrium. Given a current generator means it maintains a constant current. A current generator right now, a wire which can slide on that, a wire which can slide on that, First condition, it is in equilibrium. So definitely the magnetic force must be upwards to balance energy. And that magnetic force, we are knowing that on a current carrying wire because of magnetic field. Field is now normal to plane of this board and towards us, right? It is I into L bar cross B bar. And you can see B bar normal to this plane and L bar is now according to a given direction of current like this. So it flows now in this way. So L bar and B bar mutually perpendicular. So it's a modulus value ILB. Okay, modulus value. So it must be ILB. This is balancing energy. Now condition is we are replacing that wire with a wire of double the mass. Then see what happens. There is no change in this magnetic force, but weight is now doubled. So here we got a conclusion that mg equal to ILB. So now what happened? We have replaced a wire with a wire of double the mass. So it is now 2 mg and this is now remains same ILB. So net value how much? 2 mg minus ILB. That means F net. That net force equal to mg, right? Because mg equal to ILB. So this is mg. This is a 2 mg. So net value 2 mg minus mg. This is a downwards. And what is acceleration? Net force upon mass. Mass is now 2m, not m. That means acceleration is g by 2 downwards, right? Now see the question. How long will it take in falling through a distance equal to its length? So condition, it starts from rest, u value 0, a value constant, g by 2. Displacement is L. We have to find time taken. Then I can write S equal to half a t square, half a t square, right? So from this t value, see how much? Is 2 root of L by G, right? So like this, we can calculate. Let us see the next problem. Figure shows a straight long wire carrying a current I and a rod of length L coplanar with the wire and perpendicular to it. That means this wire and this wire both are in the same plane. Okay, coplanar. The rod moves with a constant velocity v in a direction parallel to the wire. The distance of the wire from the center of the rod is x. Find the motional EMF induced in the rod. Okay, let us see how to start. So first of all, I'm making the given diagram. This is now current carrying wire. Current is I. Now there is a wire. Its length is L. Its velocity given as V. And its center is at a distance x from this wire. Okay. So we have to find the motional EMF induced. Right. Then see what we can write. We can see different elements on this wire are at different distances from this wire. Okay. So we have tried it is E equal to L bar dot V bar cross B bar. Okay. We can see L bar, V bar, and B bar. See, B bar will be because of this current carrying wire, which is now into the board. You can see right of this wire at any point, field is now into the board. Left of this wire at any point, field is outwards, means towards us, right? So modulus value L into V into B, because all these three vectors are mutually perpendicular, right? So now what I'm doing here, I'm taking one element at a distance x, or I can say use y, because already x is given here. So I am taking now at some distance y, take element of length dy. Okay. Across that length, what is EMF induced? That is given by, that is equal to B value mu naught I by 2 pi y, because of a current carrying wire. B, L is now dy, BLV. Like this, we have to take all elements from this end to up to this end. So I am taking integration here, right? And limits. It is y equal to, I am taking from x minus L by 2. It is up to here x, right? This is L by 2. So x minus L by 2 up to x plus L by 2. Okay. Then see what we get. Let us take constants outside. Mu naught I v upon 2 pi. Remaining is integration of dy by y. That is ln y, right? That is ln y. Now substitute limits in that. So EMF induced is equal to, it is equal to mu naught I v upon 2 pi ln, see what we get, upper limit x plus L by 2 upon x minus L by 2. Is actually log A minus log B, that is equal log A by B, right? So if you simplify this, mu naught IV upon 2 pi ln 2x plus L upon 2x minus L, right? That is just taking elements. Okay. Then we have to take limits, proper limits. Then we have to integrate, right? Let us see next one. Let's see the question given. A rectangular metallic loop of length L and width B is placed coplanarly with a long wire carrying current I as shown. The loop is moved perpendicular to the wire with a speed v in the plane containing the wire and the loop. Calculate the EMF induced in the loop when the rear end of the loop is at a distance A from the wire. Solve by using Faraday's law for the flux through the loop, and also by replacing different segments with equivalent batteries. Okay, that is the question given. Let us see how to start. Right, first of all, make the given diagram. This is a long wire which is carrying current. That is I. Having here a wire loop. Shape is rectangle. its velocity given as v. This length is L and this is given as v, right? I think it is given here. Speed is a speed constant. Okay, it is with the speed v. Now we have to calculate EMF induced. Now see what we can write here. First, I am doing by taking equivalent batteries. So motional EMF is, it is L bar dot V bar cross B bar. Okay. If you focus now this length, let me take it as M N O P. For Mn and OP, velocity and L bar, they are parallel. Therefore, across Mn, no EMF is induced. Across OP also, no EMF is induced. Now it is only across MP and across NO. Okay. So if I am focusing at MP in this wire, let me take this as EMF is E1 here. And in this one, take it as E2. Then E1 equal to BLV, because magnetic field is into the boat. Length is like this, velocity normal to that. So all these three vectors are mutually perpendicular. Okay. So I can write here directly modulus value BLV. B value mu naught I by distance given as a mu naught I by 2 pi A. That is a field at this location. B L. L is now B, right? Its length is B. V. It is B, right? In the same way, coming to E2. E2 value mu naught I by 2 pi. It is A plus L, right? That is B into L into V. So EMF induced across MP, across NO. Now net value, you can see E1 is greater than E2, right? So I am taking here E1 minus E2. So in that I can take constants outside. U naught I B V upon 2 pi. Remaining is now 1 by A minus 1 by A plus, right? Then see what you are going to get. So the calculation is now U naught I B V upon 2 pi A plus L minus A. L is left. It is now A into A plus L. That is the net EMF induced. Okay. But now he's asking, calculate same thing by using Faraday's law also, right? That means, first of all, we have to find out flux through this entire loop. Then we have to take rate of change of flux. Okay. Then see what we can do here to find in that way. This is now current carrying wire. Current is I. This is now rectangle. So here I am taking at some distance. At some distance, let us take here the notations given. This is given as a, let us take at some distance, distance x, take a width now, it is dx. So our goal is here to calculate what is a flux through that entire loop. Okay. So I have taken now one rectangle here. Now flux through that rectangle, flux through that I'm taking as d phi. Okay, magnetic flux. That is equal to B value mu naught I by 2 pi x. B area equal to B into dx, right? That is area. This is now flux through that rectangle. Like this, we have to take all rectangles from where to where? From this end to up to this end. But remember, this length given as A, and that is not a constant, okay? Because it is moving. So now what I'm doing is, I'm taking this distance as y, which is variable. Then I'm taking now limits from y to y plus L. I hope you got a clarity why I have taken y here, because this distance is not fixed, because that loop is now moving. That's why it should be a variable. It is y. Now flux is equal to mu naught I upon 2 pi x b dx by dt. Wait. X is variable, right? So b dx by x. dx by x. X is not a constant. Mu naught ib by 2 pi dx by x. That is ln. That is ln limits y plus some or leave it like this ln y plus some minus ln y. Okay. So log a minus log. This is now flux. Now to get EMF. EMF equal to minus d phi by dt. Right? Or I'm taking it only modulus value d phi by dt. Focus modulus value. Then see what we get. Mu naught I b upon 2 pi derivative of log. It is 1 by x. Is 1 by y plus minus 1 by y. Right? Now in this, what is y value? It is given that when it is equal to A, what is EMF induced? Okay, now when y equal to A. So take y value here, A. Taken y value here, right? Then we get again same answer. Okay. So either we can calculate by taking as a combination of equivalent batteries, right? So here, if you want to make a circuit, okay, by replacing with the batteries, there you have to focus which end is a positive, which end is negative. Is it like M is at high potential or P at high potential? That we have to cross check. See, for that, what I'm doing here, suppose I'm taking now NO, okay, NO to decide which end is at high potential, NO, velocity right side. Field is now, because of this wire, right of this wire at any point, field is now into the board. So field is now into the board. Okay. Now focus force acting on electrons. Okay. See carefully. We are focusing force acting on electrons. F bar equal to Q into V bar cross B bar. Focus now direction. Charge of electron negative. V bar direction I cap. Okay, we have taken this is X and this is Y. Okay, so it is I cap across minus K cap. V bar is into the board. Minus plus. I cap across K cap. It is I cap cross K cap minus J cap. Means electrons will move down. Okay. So O becomes low potential and N becomes a high potential. Now same logic for MP also, because direction of field is same, velocity also same. That means we replace this with two batteries like this. This is battery 1. This is battery 2. Okay. This is E1 and this is E2. Then net value, right? E1 minus E2. Okay. So I hope you got the clarity.